In this video, we will be looking at inverse functions. We're going to find out what are inverse functions, how to find the inverse of a function, and how to graph inverse functions. But let's just start out with a review. Remember our definition of a function. A function is a set of ordered pairs where for every x value, there is a unique y value. Remember, we used the vertical line test on graphs to determine if a graph is a function. In other words, for every x value, there is a unique y value. So let's look at these three graphs. Are they functions? Well, the vertical line test says for every x value, there is a unique y value, which means every time I draw a vertical line, it should only pass through the function one unique spot. So yes, this is a function. The next one, well, you can draw many vertical lines and it definitely crosses through the graph more than once, as in it's not unique. For example, when x is 1, we have a y value of 4 and a y value of -1. So 1 is being mapped to two different y values. So this is not a function. The third graph is a line. It is a line with some type of positive slope, and no matter where I draw a vertical line, it only passes through this graph one unique value. So this is, yes, this is definitely a function. Now we're going to look at one-to-one functions. A function is said to be one-to-one if each y value corresponds to only one x value. So we're kind of going backwards. So for every y value, there's only one x value. So since we're kind of reversing it, we're going to be using the horizontal line test to see if these functions, so keep in mind, these are already functions. So all of these three in front of you would pass the vertical line test because they are functions. Now we're going to see, are they one-to-one functions? So if I draw a horizontal line, does it intersect the function in more than one point? Yes, it does. So this is not one-to-one. It is a function, but it's not a one-to-one function. All right, so what about this one? No matter where I draw a horizontal line, it only intersects the function in one unique spot. So this is, yes, this is one-to-one. Same thing on this one, no matter where I draw a horizontal line, it only intersects the graph in one unique point. And so yes, this is a one-to-one function. All right, so a function passes the vertical line test. A one-to-one function also passes the horizontal line test. Why is this important? Well, it brings us to the topic of inverse functions. Only one-to-one functions have inverse functions. A function and its inverse can be described as the do and the undo functions. A function takes a starting value, like an x value, performs some operation, creates an output. The inverse of this function takes the output answer, performs some operation, and arrives back at the original function starting value. Let's just talk about inverse operations. So if you take the number 10 and you multiply it by 2, you get 20. So this was our output. And if you take the inverse operation and divide it by 2, remember, multiply, divide, you start back at the original value. Those are inverse operations. It gets you back to your starting point. That's what inverse functions also do. Let's just look at this function. Now we know this is a line, and so the domain is all real numbers. But I'm just going to pick some random values for x. Remember, our x's, that's my domain, could be anything. What does it map to? Meaning, what is my output? Okay, so remember, this is my input, and I just picked some values. What's my output? So again, I replace x with -2. So 2 times -2 minus 3 is -7. I put in 1, I get -1. And if I put in 0, I get -3. Now, the inverse. That would mean that I take these values, my output, which now becomes my input for my inverse function, and I need to go backwards and end up where I started out with. So what would I have to do to -7 to get to -2? Well, there's lots of things, and we're going to investigate that a little bit in the video. So just hold on to that question. The definition of an inverse function. If f is 1 to 1, remember it has to be a 1 to 1 function, then this symbol is the inverse function of f. Now that -1 is just a new symbol, but it's f, it's the inverse of the function of f. Again, be careful of that notation. F inverse of x. So this says f of f inverse of x equals to x. So my function and its inverse undoes everything and gets me back to my input for every x in the domain. And, here's a big and, f inverse of f of x also gets me back to the original starting point. And you're going, wow, hold on. Well, remember, we just did composite functions. So these are two functions, and we're composing them, and we should get back to where we started out with. And that is our first objective. We're going to verify inverses. So it says find f of g of x and g of f of x, that's a review of our composite function, to determine whether each pair of functions, f and g, are they inverses of each other. Okay, so I'm going to find f of g of x. So that's f of 4x plus 9. Remember, we replace g of x by its definition. Then we go to the f function, and everywhere there is an x, I'm going to replace it with 4x plus 9. So I have 4x plus 9, that's in place of x, minus 9 divided by 4. Now the arithmetic should be very easy, but you need to show all your steps. I know that 9 minus 9 is 0. And again, I'm going to write that step down. And then I can divide 4 divided by 4, and I get x. So can I conclude that these are inverses? Not quite yet, because I now have to do it the other way. So I need to find g of f of x. So same process. F of x is x minus 9 divided by 4. So wherever there is an x, I'm going to write down x minus 9 divided by 4. And again, show all your steps. So here, those divide out, and I'm just left with x minus 9. And yes, we could have done all that in our head, but again, showing all of our steps, that's 0. Are these inverses of one another? Yes, they are, because the function evaluated at g of x got me x, and going back the other way also got me x. Okay, here's our next one, f of g of x. So that's f of 3x minus 2. So wherever there is an x, I'm putting in 3x minus 2 and showing all my steps. Showing all my steps. So let's see, I have 3x plus 1 divided by 2. Can I do anything else? No. We can stop right there. They are not inverses. I didn't end up with x. But just in case you started out the other way and did this, So I'd have g of x plus 3 divided by 2. So that would be 3 times, x plus 3 divided by 2 minus 2. Would I have gotten anything different? Well, got a different answer, but it wasn't x. So these are not inverses. Again, you could have stopped here and made that conclusion because you didn't get x. Let's do this last example. So we have f of g of x. So f of 2 divided by x plus 5. So wherever there is an x, we're going to put in 2 over x plus 5. Right? Again, slow and steady. 5 minus 5 is 0. What does this mean? This means 2 divided by 2 over x, which is 2 times x over 2. Remember, when you divide by fractions, you multiply the reciprocals, and that is equal to x. So that's looking good so far. Okay, let's go the other way around. G of f of x. So let's see. F of x is 2 divided by x minus 5. So we have 2 divided by this stuff. 2 over x minus 5. That's in place of my x. Oops. And then plus 5 is separate. I drew that line too long. This part right here, we're going to do the same thing we did here. This is 2 divided by 2 over x minus 5. So we're going to say 2 multiplied by x minus 5 over 2. Ah, that's looking much better. I can reduce that, and that goes to 0. And this is x. Yes, these are inverse functions because f of g of x is equal to x, and g of f of x is equal to x.